13.9. This is on Lagrange multipliers. So the goal of this section, we've been doing some max-min problems. The goal of this particular section is very specific. So the goal is to find the maximum and minimum of a function. Say f of xy with a constraint, and the constraint is an equality. So let's just sort of look at a visual example before we talk about a method. For example, we could say, suppose that the point xy is constrained by x squared plus y squared equals 9, which means it's fixed on a circle. Cannot get off the circle. Right? So then we could say, for these x comma y, let's let f of x comma y be x plus 3y. Then we might ask, how big / small could f be? Right, so what's happening here is, visually, this is actually a really good example for a visual understanding, is we're constrained by a circle, so we're stuck on, say, let's make this purple. We're stuck on that purple circle, cannot get off. Its radius 3, f of x squared plus 9y squared equals 9. And if you notice, at different points on the circle, f has different values. So at, say, 3, 0, f of 3, 0, in this case is 3 plus 3 times 0 is 3. If you're down here, f of 0, negative 3 is negative 3. It's smaller. Sorry, I did my math wrong there. X plus 3y, this is negative 9, still smaller. And so you could sort of test different points, right? Like, it doesn't have to be a nice point. It could be a point right here. You could look at f of this, whatever that point you chose. And the question becomes, what's the biggest and the smallest you can obtain? What's the max and min f we can get? So there's a theorem associated to Lagrange multiplier. So I'm going to state the theorem as a fact. I'm not going to prove it. And then we'll look at sort of how this theorem plays out in terms of examples. So let's say a theorem associated to Lagrange multipliers. You could call it the Lagrange multiplier theorem or whatever you want. So what it says is the following. It says, suppose that xy is constrained, say, by g of xy equals c. So just for reference, I didn't list the g in the previous problem. So in the previous problem, this guy would be my g. G of xy equals, that would be my c. So the constraint is also, in a sense, given by a function. So c here is a constant. And now the way the theorem works is as follows. It says, if a function f of xy has a max or min on the constraint, you could say officially subject to the constraint, but we can say on the constraint if we're thinking visually, at the point xy. So then what happens then at that point? So what turns out to be the case here is that the gradient of f equals lambda times the gradient of g for some number lambda. So basically what's going on here is that the level curves of f and g, or the normal vectors, how many different ways to think about it, have to be parallel to one another. And when two things are parallel, they're a scalar multiple. That's what's going on here. And there's still some deep theory going in here. It's not screamingly obvious. It can be reasonably explained with a picture in 10 or 15 minutes, but it's not overly relevant for doing the calculations. So now, just to keep in mind what this means is to say that these are equal, right? So lambda f, remember what this means. This means f sub xi plus f sub yj, and lambda g, this means g sub x I plus g sub y j. So to say that these are equal, or to say that lambda f, nabla, sorry, I keep saying that lambdas and nablas confused. To say that nabla f, the gradient of f, is lambda times nabla g, means that f sub x is lambda times g sub x, and f sub y is lambda times g sub y. So what this all means in terms of finding the maximum minimum, like the practical application, is as follows. So we can phrase this as let me give this as a thus, and then we'll turn this into a method. Right? If it's the case, if f has a max min, say max or min at an xy, let's say, just to be clear, subject to the constraint, with constraint, let's say with g of xy equals c, and three things must be true. First thing, f sub x at xy must be lambda g sub x at xy. F sub y at xy must be lambda g sub y at xy. And of course, we have to satisfy the constraint. So g of xy must be c. So what this tells us for a method, now let's be cautious. It says if it has a max or min. It doesn't say that if these three things are true, then you absolutely have a max or min. But what you do is you then solve these equations. This is a system of equations. You get the x's and y's, and then you simply plug them into f and see what the biggest and the smallest of those values are. So we solve this system. Let me label this, make sure it's clear what we're solving. This is a system right here. We solve this system of three equations, three unknowns. The unknowns here are x, y, and lambda. I'm going to make a comment about the lambda in a second. For each resulting point, x comma y, we plug it into, let's say we plug each into f and pick out the max if we want a max. Let's say if we need a max, pick out a minimum if we need a minimum. In other words, if those things are there that we're looking for. And just a little note before I do an example is the lambda is just sort of this variable. The lambda is actually what's called the Lagrange multiplier. So you may find lambda as you go through this. It doesn't really matter, right? So really finding lambda isn't important. It just may come up as part of the process. The goal is x's and y's. So what I'll do is I'll do the example that we began the conversation with, and then I'll just do a few. And for what it's worth, something to consider is the hardest part of this entire process is solving this system right here. Right? That's the thing that can be confusing, because everything else, right? you take some partial derivatives, that's pretty easy. You write down the system, that's pretty easy. You solve it, that can be a pain. Once you solved it, you're just plugging things into F. So this is the tricky part. So what I'm going to do is, there are a few different ways that you can solve systems of equations, and I don't want to say this is how you need to do it, right? Like, it's a system of equations, it's an algebraic problem, it's a pre-calculus problem, however you want to think about it. But I'll go through a method which will pretty reliably work so that you have something to go to. But any other method you can come up with is fine, as long as you get the solutions. So, example, we're going to find the min and the max of f of xy equals x plus 3y. This was the one at the beginning with, let's say, x squared plus y squared equals 9. So the first thing we do is we set g of xy, just so we're clear on what g is, to be x squared plus y squared. And we write down the system. So the system is going to be, I'm going to try and make this fairly compact so we can fit everything in this one panel. So I have f sub x, which is 1, equals lambda times g sub x, which is 2x. And then I have f sub y, which is 3, equals lambda times g sub y. And then I have just the constraint itself. So this system right here is what we need to solve. The nice thing about doing this in software is the computers are very good at this. So this is just this system. It's good to have it on the page, and we can refer back to it. So here's one way that will pretty much reliably work. Is let me label these, say, 1, 2, and 3. Or let's say A, B, and C. So I'm going to take A and B, and I'm going to multiply the left side of whatever it takes to make the left sides equal. Right? So make the left sides of A and B identical. So in this case, I can multiply A by 3. So A says 1 equals lambda times 2x. So that tells us that 3 is lambda times 6x. And B, I can leave it alone. And then what we can do is we can equate the two. In other words, if 3 is lambda 6x, then 3 is lambda 2y. Then lambda 6x is lambda 2y. Now, it's really, really tempting to cancel the lambda, but lambda might be 0. So I want to try to not cancel anything. So what we can do is we can cancel the 2, of course, and then we can bring everything on one side. So I'm going to cancel the 2 and bring them to one side and factor out the lambda to make sure my x's look different than my lambdas. So now we can say either lambda equals 0 or 3x equals y, or if you like, y equals 3, or 3x minus y equals 0, or y equals 3x. Now, then we go back to our system, and we notice something. If we go back to A at the very, very beginning, if lambda is 0, then A says that 1 equals 0. So we get 1 equals 0 times 2x. This is a big no, right? 1 is not 0. So that's gone. I throw that out, right? Thus we know y equals 3x. And then what I do is I'm going to put that into C. So what we get is x squared plus y, which is 3x squared, equals 9. So this is 10, oops, sorry, there should be 3x squared in there. So we get 10x squared is 9. So x, if I solve for it, is plus or minus. So I basically have the square root of 9 over 10. So that's 3 over root 10. Now, we know that y is 3x, because that's what we're doing. So y is 3 times this. So we get 2 points. So points are 3 over root 10, and then 3 times that, and negative 3 over root 10, and 3 times that. So I test those. Right, so I take f of the first one. So remember, f way back at the beginning, we sort of lost track of it, is x plus 3y. So this is x plus 3 times y. This is 30 over root 10. And if we do the same with the other one, we get negative 9 over root 10. We get negative 30 over root 10. So then what we do, I apologize for cramming this in, but I don't want to erase anything so we can reference everything, is we look at the values that result. There are 2 values. Now, there may be more than 2. Just for reference, you might get 4 or 6 or something. But what you do is you look amongst all those values and you pick out the max and the min, because we want the max and the min, so we can look, we can be like, well, this is clearly the max because it's the biggest. This is clearly the min because it's the smallest. So I'll do a couple more so we can see what else happens. But again, the tricky thing is always this process that we go through right here of solving this system. That's the bit that can be confusing, right? And a reliable way is always to make those left sides identical and then set them equal and go from there. It'll pretty much work most of the time. Now, again, like I said, if you've seen other ways, especially students who are in, say, economics, there are ways that this is done in economics. Economics has a lot of Lagrange multipliers problems because they're maximizing profits, minimizing costs with constraints, real-world constraints. So there are different approaches to solving these there, different ways of writing it. You're absolutely welcome to use anything that you want as long as you're basically following the fundamental methods of Lagrange multipliers. So let me do this. Let me clear the screen. Start a new example from scratch. Let's do an example. We're going to find just the min of f of xy equals xy with y equals 2x plus 4. And I'm going to make a comment at the end of this problem about why we're just finding the minimum. But this is a good problem because we can write a good picture of this, right? Not all these problems have easy pictures, and the pictures are totally not necessary. You don't need the picture to do the problem, but when you can draw a picture, sometimes it helps people really understand what's going on. So here the constraint is a line, y equals 2x plus 4. So that line is, say, we'll make it purple. That's the constraint. We are stuck on the line. Right? That's this guy right here. So we're stuck on the line. And what we're saying here is, hey, if f of x equals xy, how big can this be? Or how small, rather? How small can f be on the line? Sorry, I changed from uppercase to lowercase, which looks terrible, but there we go. So the first thing we do is I need to rewrite the constraint because it needs to be equal to a constant. So we rewrite this as y minus 2x equals 4. Now, sometimes books will move the 4 over as well and make it equal to 0. They might write y minus 2x minus 4 equals 0. It doesn't matter. You could also maybe move the y over and write 2x minus y plus 4 equals 0. Doesn't matter. The solution will be the same. You might have some plus or minuses that change. You might have some constants that spring up. But as long as you get the variables on one side and a constant on the other side, you're good to go. Right? So this becomes our g of xy. That becomes our y minus 2x, the way that we've done this. Right? So then the system, again, is f sub x, which is y, equals lambda times g sub x, which is negative 2. We'll call that a. Then we have f sub y, which is x, is lambda times g sub y, which is 1. That's b. And then we have the constraint itself, which you can write it as y minus 2x equals 4. You can write it as y equals 2x plus 4, as long as you just drop down the constraint. So now this is the system that we need to solve. So again, there are multiple ways to do this. I'm just going to use the exact same approach. If I need to make the left and right sides of a and b the same, I'm going to multiply a by x and b by y. So b, let me do it this way. A, this is y equals, we rewrite it, negative 2 lambda. This becomes xy equals negative 2 lambda x. B, x equals lambda. This becomes xy equals lambda y. And again, I did that because these are now identical. So we can make these two identical. So thus we can say that negative 2 lambda x is lambda y. We can get everything on one side, so let me get things on the right, just so we don't have minuses lying around. So lambda y plus 2 lambda x is 0. Again, I don't want to divide by lambda because lambda might be 0, so I factor it out. So lambda equals 0, or y equals negative 2x. Now, take a look at this case, right? If lambda equals 0. Now, interesting fact is it's not uncommon that lambda cannot equal 0, but we always have to check it out. We could get something. So if we go back to the system, if lambda equals 0, then A says that y equals 0 times negative 2, which is 0. That's okay. No problem there. No contradictions. B says that x is 0 times 1, which is 0. No problem there. But C has a problem with that because C says y equals 2x plus 4. So that would then become 0 equals 2 times 0, that's an x right there, plus 4. This is a big nope. So we can throw that out. Then we go back to if y equals negative 2x. So if that's the case, I can put that into C. So if we do that, we get negative 2x equals 2x plus 4. So add the 2x to both sides, or subtract rather. I get negative 4x is 4, so x is negative 1. Then y is equal to negative 2x, which is 2. So we get a single point. Now, I don't need to really check it to know that it's the minimum. It's just the 1 point, but we can check it anyway, because now we exactly know how small f can be. Right? This is where it is that small. So f as the product is negative 2. So now we're done. Now let me just sort of comment here. Let me go back to this picture. I'll redraw it so I don't have to draw on the left-hand side. What this is saying is, in order to make us f as small as possible, you would go to negative 1. So this picture is sort of drawn badly. Let me do this. It's not really drawn to scale. Erase the purple line and redraw it. So it's got a y-intercept of 4. Let me put some tick marks in. I just want some precision here. So we draw the line in. It's got a slope of 2 and a y-intercept of 4. So it's going like this. And what this solution is saying is, if I want xy to be as small as possible, I would go to negative 1, 2. I would go right here. So the smallest xy is here. Now, you might wonder why I didn't ask for maximum. So if you look at this problem, you can go up the right-hand side of the graph. If you go up here, x and y get really, really, really big. And xy therefore gets arbitrarily big. Right? So as x and y to infinity, f goes to infinity, because it's the product. And likewise, if you go down here, as x and y go to negative infinity, f goes to infinity because it's the product. So in this particular example, there's no maximum. Right? The minimum is at this point right here that we just looked at. And there is no maximum because as you move away, f just gets bigger and bigger forever and ever. So in that case, that's it. So let me clear the screen, do one more example, and then we'll call it a day. So for example, let's find max and min of f of x, y equals x plus xy with x squared plus y squared equals 1. So for what it's worth, I'm sticking with pretty simple functions and pretty simple constraints because these problems can get extremely hard. Like if you make the function x squared y plus x, then the derivatives get terrible and the system of equations gets awful. And this isn't really as bad when you can use technology to solve these, but it's still going to be pretty terrible. I mean, systems of equations are not easy things to solve, and you end up using methods of approximation to do it. So we're going to stick with really easy ones so that we understand the method. Right? The fact that a complicated one might be done with software doesn't really, like, that's great. We can accept that, but we just want to make sure that we know how we're stepping through these. Right? So I'm not going to worry about a picture for this. Again, we're stuck on a circle, x squared plus y squared equals 1. Let's just go through the method. We're going to set g of xy to be x squared plus y squared. And we're going to write down the system. So it's f sub x, which is 1 plus y, equals lambda times g sub x, which is 2x. And we have f sub y, which is x, is lambda times g sub y, which is 2y. And then we have the constraint itself. So that's our system that we want to solve. Make sure I put a C there for the third one. So again, same approach as before. I'm going to multiply, in this case, a by x and b by 1 plus y. It looks sort of messy, but it's not so bad. So a, this guy, this tells us if I multiply by x, is lambda times 2x squared. B, this one, if I multiply by 1 plus y, you get lambda times 2y plus times 1 plus y. So I set those equal. In other words, the right-hand sides. And again, move everything to one side and factor out the lambda. Now, we can also factor out a 2. We can actually divide by 2 on both sides. Let me just throw out the 2. So get everything on one side, divide by 2, get everything on one side, and factor out the lambda. So then either lambda equals 0 or this mess equals 0. Come back to that in a second. Right? So let's look at lambda equals 0. Right? If lambda equals 0, let's go back to A. What does A say? So if lambda equals 0, the right-hand side is 0. So I get 1 plus y is 0 times 2x. So that says that lambda is negative 1. Right? Because 1 plus y is 0. So y is negative 1. Not a problem. Right? B says that x is 0 times 2y, which is 0. So x is 0. That's okay. C then says x squared plus y squared equals 1, right? Well, 0 squared plus negative 1 squared is 1. That's okay. So what happened here? Like, when lambda is 0, we got a point. We got 0 and negative 1. So, sort of, that's a point we need to keep in mind. I'm going to put a green box around it. Just like, hey, this is a possible solution. Like, it's good to go. Like, we may need this. So then we look at the other option, which is if this mess is 0. X squared minus 2y 1 plus y equals 0. So I'm going to tidy this up a bit. I'm going to write this as x squared. I'm going to move the stuff to the other side, and I'm going to distribute. So when we distribute, we get negative 2y minus 2y squared. Actually, hold on. I realized something here. Back in the system, when I moved things over, I canceled a 2, and I didn't cancel it everywhere. So just to clarify, back, I'm going to sort of modify the left. That 2 is gone, because we canceled the 2's. And that 2 is gone. Otherwise, we're okay. This 2 is gone. That's not a tragic mistake. So make sure that's all good. Yep, 2's were canceled. Just forgot to cancel one of them. So now back up here, I distribute the y and I move them over. Now, I could solve for x, but I'm going to plug this into c, and c has an x squared in it. So we're going to put this all together, and this is the plus. Try not to make it's worth noting, actually, this is a humorous place to put this. The biggest thing that happens when we're solving these systems is stupid little algebra mistakes, as I'm evidenting right here. So just keep an eye out, like double check your calculations, because otherwise things can be a mess here. So now I'm taking my x squared, which is y plus y squared. I'm putting it back into c. This is what we get. So now this becomes 2y squared plus y minus 1 equals 0. This is particularly nice at factors. 2y minus 1 times y plus 1. Double check my algebra again, so I'm not making tragic mistakes. So either y is 1/2 or y equals negative 1. Right? Now, we also know that x squared plus y squared equals 1. So we could say if y is 1/2, then x squared plus y squared equals 1. So x squared, so this is 1/4, I subtract it, we get 3/4. So x is plus or minus root 3 over 2. And if y is negative 1, then x squared plus y squared is 1. So x squared is 0. So x is 0. So in the first case, let's be clear here. In this case, let me do this in green, because we did the other points in green. In this case, we got 2 points, plus or minus root 3 over 2, comma 1/2. And in this case, we got 1 point, which you'll notice, coincidentally, because this sometimes happens when you're dealing with systems of equations, is the same point that we got earlier. Right, so we've got 3 points here. We've got plus or minus root 3 over 2, and we've got comma 1/2, and we've got 0, negative 1. The fact that that 0, negative 1 came up twice is no big deal. It just came up twice. We only need to plug it in once, of course. That's just the way it is. So then we test them. So we take f of root 3 over 2, 1/2. We plug that in. So remember, f of xy is x plus xy, way back at the beginning up there. We sort of haven't really used it once it vanished into the system. So that's x plus x, y. So I'm going to simplify that a bit because it'll make things a little nicer. So the second one is root 3 over 4. So this is 2 root 3 over 4. So I get 3 root 3 over 4. The next one isn't so bad. This is a negative root 3 over 2, 1/2. This is negative root 3 over 2 plus xy, which is minus root 3 over 2, 1/2. So this is just the negative of the one before it. And then last but not least, this sort of straggler, 0, negative 1. X plus xy is 0. So if we look at all of these, all we do is we pick out the max and the min. So this guy is on max, and this one is on min. And this other point, for what it's worth, it's neither. It's just a point that came up in the system. really what's happening, it's sort of like a weird kind of inflection point, but it's not something that we're interested in. It became not relevant, but we still have to check it. It's still a solution. But this is just neither. You don't need to write that. This is just so we have a reference to it in case you're curious. That's just the resulting nothing. So that's the third problem, and that's the end of that section on Lagrange multipliers.